to speak in this conference. So today I'll be talking about construction of quasi-periodic solutions to nonlinear random Schrödinger equation. This is a joint work with Bourgain. And as you see as the talk goes along, that many aspects of this problem has some connections with some of the talks you have heard earlier in this conference. So I'll start with the linear problem. I guess many of you know what a Schrödinger equation is, but yes. Okay, but I'll write it nonetheless. Okay, so the Schrödinger equation is I d dt psi equal to minus Laplacian plus v, plus v psi, and it's an RD cross 0 infinity. This is time, or ZD cross 0 infinity. And so let's say on RD, everyone knows what the continuum Laplacian is. On ZD, let me take d equals to 1. And in this case, Laplacian uj, this is perhaps you're a bit less familiar with the discrete Laplacian, that's why I'm writing it out. And it's just a tri-diagonal matrix to form. I've taken the diagonal part out, 1, 1. Okay, so this is your discrete Laplacian. And when v equals to 0, you have a free particle, right? And the basic solution of the Fourier series psi is ei k squared t plus kx. Okay, so this is an RD. And when v is periodic, oh, sorry, I'm skipping ahead of myself. So here the states psi, they are extended. Psi squared is a constant, right? So the quantum mechanical interpretation is the probability of finding the particle at x at time t. It's constant, so it's extended. So another example is when v is a periodic function, you also have psi squared is also, psi is also extended. So these are scattering states, right? In this case, since we look at potentials which are time independent, the time evolution can be just reduced to the spectral study of the Schrödinger operator H equals to minus Laplacian plus V. And in both cases, the spectrum of sigma is absolutely continuous. So now I'm going to talk about what's a random Schrödinger. So random Schrödinger just means that V is a random variable. So now I'm going to specialize, or what's going to follow, I'm going to specialize to ZD. Okay. So in this case, V, so Vj, J in ZD, I take it, for example, as a family of independent, identically distributed random variables. Okay, so just to fix ideas, To fix ideas, I take Vj can take only two values, +1 or -1, with equal probability, for example. And So you can just imagine in this case you have a discrete Laplacian plus a potential at each point, which could take the value either +1 or -1. Okay. And now what am I going to do? Now I'm going to add I want to state some theorem in the linear case. So I need a parameter, and I add the parameter lambda in front. And so in this case, the point is the following. The point is called what's so-called Anderson localization, is that when lambda is very large, the spectrum sigma h is almost surely pure point. Okay? Pure point just means only contains L2 eigenfunctions, and it's dense. So the emphasis is put on the word dense. So it's dense, almost surely dense pure point, evidently with some conditions on the distribution of the random variables, the potentials. Okay, I won't state here. With exponentially localized eigenfunctions. Okay. So again, to fix ideas, you assume, for example, let's assume the spectrum is in the interval 0 and 1. And you just imagine that your eigenvalues are, for example, all the rational points. Okay? All this is just to fix ideas. So what I'm mainly interested in, of course, is evolution in time. In this case, since it's linear, and the potential is time independent, the evolution in time is very simple, right? So, and arbitrary, so the word is arbitrary, okay? Localized wave packet initially, right? Localized initial wave packet remain localized for all time. Okay.
Can you write larger, please?
Sorry. Oh, I should write larger. Okay. I'll do that starting from the next line. Okay. So it's right. This is just linear spectral theory. Okay. So. And arbitrary, the word is arbitrary here, localized initial wave packet to remain localized for all time is just eigenfunction expansion, right? Okay. So, now I write larger. I.e., solutions are quasi-periodic in time. And if you're fussy, I'll say almost periodic. Okay. Almost periodic just means you can have an infinite number of frequencies. Okay. So what I just quoted is the result of Fröhlich-Spencer around 1983. Okay. The main novelty in this is that H is pure point but dense. Okay, so which means that the linear problem already has small divisors, yeah? Okay. So if you use the KM language, you have a dense set of invariant tori already. So that's the starting point. And the main property that we used to prove such localization is a separation property, which I'll state because it's very important. This is, in a way, the only property one uses in the nonlinear case. It's a separation property.
What dimension?
No, it's in all dimensions. So as you'll see, we don't use any integrability of the system. No. It's a separation property. So the main property is the following. So I first state in word that you see, if you look at the spectrum, you're basically lost because it's dense. You know, there's no gap anywhere. So you can't look at the eigenvalues. You have to look at the eigenfunctions. Okay, so this is the main point. Okay, so if you stick with spectral language, you have to look at local spectral density, right? So eigenfunctions which correspond to eigenvalues that are close live very far apart. Okay. So let me be more precise here. Let me be more precise. I mean, this is analysis, so there's large and small. Okay, but in this business, large and small is relative to the scale. Okay, so what I mean is the following: is that if you take a scale L, and I take two blocks within the scale, so this is L with C some greater than 0, okay, and another little block of size L 1 over C. And if you restrict your Hamiltonian to this little block and that little block, okay, then what you have is the following. Is that remember that I have a probability here, right? Because my potentials have some probability distribution. Okay, so the probability that the distance of the spectrum sigma h1, this here I call it h1, here I call h2, sigma h1, sigma h2 is less than 1 over LP. L is this L, okay, is less than 1 over LQ for any two blocks that do not intersect. So what this says is that I fix for myself a scale L, and I take blocks which are at the scale L1 over C. Then all the little blocks inside this big block which do not intersect have spectrums that are far away, so they do not resonate. Okay, so that's the separation property, which is the only property that we use when you do the construction for the nonlinear problem. Okay, so this is the main property, which, by the way, holds for other ergodic operators, like when you have a quasi-periodic potential. Or in the deterministic case, typically the separation property that I'm talking about will be given by number theoretical considerations.
Is there any relation between C, P, and Q? Or is it
Oh yeah, there are relations, of course. Yes. Yes. Okay. So now finally I come to the description of the nonlinear problem. Okay, I cannot stress. Excuse me?
You said that the probability is small.
Yes.
It doesn't look small.
Did I put things in the wrong sign, or did I put my head in the wrong way? Distance less. Oh, sorry. Right? No, I want it to be small. So the probability of this to be small is small. Yes. Thank you very much. Okay. So this is the main property that one needs. Okay. Now the nonlinear problem. I rewrite the Schrödinger I dt u equals to Laplacian plus v u plus u 2p u, for example. So again, I'm in the discrete case here. Okay, so what I have done is I've added a nonlinear term. So the physical interpretation comes from, well, taking the electron-electron interaction into account, or whatever you call it, okay? And what I want to say is here I'm just taking the simplest form. You can take a convolution operator. It doesn't change anything, okay? And it's NAP here. And D is not, doesn't have to be, it's NAD. Okay? So what I want to stress is we do not perturb away from the integrable system. So now, permit me to add some parameters. I add epsilon here, right? So I add epsilon here, and I add delta here, obviously. Okay? So epsilon is just 1 over lambda before. Okay, delta is a small nonlinearity. So, main question. Main question is persistence of Anderson localization, i.e. what I stated earlier, persists for small delta. Okay, so the question is whether this linear phenomenon is stable under certain conditions, or in other words, the existence of quasi-periodic, time quasi-periodic solutions to this equation. Result. I first state result in words, and then I'll give a more precise statement. The result is there indeed exist time quasi-periodic solutions. So in my notes, I arbitrarily gave this equation number 2, okay? So there exists time quasi-periodic solution to 2, okay? For, now this is the key word, for carefully, right? Recall that I stressed the word in the linear case is that was arbitrary. Okay, where was it? Yeah, so in the linear case I stressed for the adjective arbitrary. Here it's for carefully. Yes, for carefully chosen initial localized conditions. Okay? More on this later. So now I'm going to give you a slightly more precise version. More precisely, so what we do is the following. I take my initial condition U0 equals to AK delta JK. Excuse me for the subscript. Oh, and the subscript, I do not have much choice. Okay, but in this case, I can get rid of the subscript j, ak delta k x k equals to 1 to nu. So to be the initial condition, okay? So I identify jk with k in ZD. Okay, so what you do is the following. Here is my ZD. Here's my ZD. I have the potentials which sit on the sides of ZD, and I excite null of them. Okay? I excite, let's say nu is 5. I excite 5 of them. So I have 5 sites which I excite, something like this. Okay? The rest is frozen. Okay? My initial condition is I have, I excite one of them. And so here note, when epsilon equals to delta equal to 0, so this is when t equals to 0, u0 xt evolves in a very simple way, right? A k e I v k t delta k of x. You agree, right? Because in this case, my operator is just a multiplication operator. H is v, okay? HU equals to VU, right? So this is quasi-periodic in time, yeah? Good. So 2 points. Yeah, so what I state now, so this is a, so I'm going to state the result. So this is a work with, program. And so now I take lambda 0 in ZD large enough so that the set k equals to 1 to nu, is containing lambda 0. So this is my lambda 0. So I take a box which contains all the excited points. Okay, so this is my lambda 0, large enough. And for the expert, lambda 0 also depends on the power of the nonlinearity. Okay, the larger the p, the larger the box you take. But this is a side remark. I take a box which contains all these sites. 2, I assume the linear operator h equals to epsilon Laplacian plus v has the separation property. Separation property in ZD, the complement of lambda 0. So, which means that, more precisely, that so you take at scale n, you take lambda 1 size n 1 over c, right? Like previously, L has been replaced by n. And lambda 2 also the same size. And lambda 1 intersect lambda 2 is empty. Then I have the property that the distance between the two localized spectrum are larger than E minus n E minus n to the power beta. Okay? When beta is greater than 0, less than 1. Okay? Okay. So as I was saying earlier, this space large and small is relative to the scale. Okay? So bigger than this is big. Smaller than that is small. Okay? It's crucial here. Okay, 1, 2, then I... Here I'm making deterministic statement. Okay? I'm just saying I'm abstract from this separation property, which says that at a certain scale, if you take two small blocks that do not intersect, their spectra are far away, okay, far in this sense, okay? And random potential is one of the easiest ways of realizing this property, okay? And other operators like quasi-periodic operator also has this property. And in the deterministic case, you have to resort to more to number theoretical arguments. Okay? So this is the easiest case in some sense. So 1, 2, and now I need a third. So essentially, you need a separation property. So third, and I should say that for people who work on nonlinear equations, you all know that you need some parameters in the problem. So the potentials I have taken of these 4 sides are the parameters of this problem. Okay. So dk k equals to nu, subset R nu is the parameter set. Okay, which means I'm going to vary them so that I'll be able to construct time quasi-periodic solutions. Okay, so now I come down to the statement. So there exists a set V in R nu. No, actually, I should Cantor set. Okay, so this is how careful you have to be. It's a Cantor set. The complement of which has measure, okay, going to 0 as epsilon plus delta going to 0. Okay? Because when epsilon plus delta equals to 0, well, you have the whole thing, right? It's the linear problem. Going to 0 such that there exists omega, which are the modulated frequency due to nonlinearity, which is a function of V, and A is the amplitude of the linear thing, of the initial condition, okay? So there exist modulated frequencies omega, which are smooth functions on R nu. Particularly omega is slightly modified from V plus O epsilon plus delta, such that U x t equal to sum U hat J n E I n dot omega t delta J x, and in Z nu J in ZD I'll explain on this picture what this theorem says in a minute. With U hat k ek equals to ak is a solution to 2, and moreover U hat jn dk exponentially away from k ek. I'll explain on the picture. K equals to 1 to nu equals to S, the singular set. Okay, so first of all, what you see is that you have constructed indeed a time quasi-periodic solution. Okay? This is time with new frequencies. So what it says is that to begin with, I have my linear problem, so I have my ZD plane. Excuse me for using the word plane. I have my ZD plane, so my linear problem is on ZD. I excite 4 modes. The rest, they are frozen. There's nothing, okay? Now I turn on the nonlinearity, and the initial condition, this wave packet is going to spread, okay? But since you're working with a nonlinear problem, it's not sufficient to work in ZD. What you have to do is you also have to add the Z nu directions, which are the higher harmonic direction for the higher harmonics. Okay? Because the higher harmonics come from the nonlinearity. I'll explain a bit later. So what it says is that it's going to spread both spatially and also in the higher harmonics direction. Okay? But nonetheless, it remain exponentially localized to the initial wave packet. Okay? And for the linear problem, it's sufficient to work on ZD, but when you go to the nonlinear problem, you don't have a choice. You immediately have to work on ZD plus nu. Okay? Because the nonlinearity couples all the modes. So this is the discrete. So the analog in the continuous case, if you, I guess for most of you who, I guess you're more sane in the sense that you work with continuous Laplacian. So if you're more familiar with continuous Laplacian, you really should think the analog is that you're working on a torus TD, okay? In that case, if you put on the torus, it has a complete set of eigenfunctions, right? Okay, and in this case, I just put myself right away on the lattice. Okay, so the continuous analog is really the continuous Laplacian on the torus. Okay. And I want to make one propaganda for random Schrödinger. Is that, as I was saying, in such problems, you always need a parameter, right? The parameter here is the potential, okay? So random Schrödinger is, in a way, a natural setting because it is a problem which, to begin with, is a problem with the parameter, yes? The potentials are moving. Okay. So now I go to a sketch of the proof.
Excuse me, the lambda knot intervenes in the result.
Excuse me?
Does the lambda knot?
What is lambda not?
Lambda 0.
Where's lambda 0? Well, you know where it is. I don't.
Box that you have where things are compact.
Yeah. I just take it large enough to contain the initial mode, and also the larger the p is, the larger you have to. You see, the p is the comes in when the Fourier transform the convolution. Yes.
I don't see where it appears in the.
Because all these statements are for epsilon delta small enough, so it's hidden there. Yes.
You said that the higher harmonics were
Yes.
excited, and so U hat does depend on T.
U hat is the Fourier transform. Excuse me.
Higher harmonics.
Well, sorry, it's n dot omega. It's the higher harmonics. Yeah, and you see, without the nonlinearity, n is always 1, right? You're always one of the basis vectors for Z nu. Yes. Yes. Okay, and you see that the omega is modified. Okay. All right. So I come to the sketch of the proof. Sketch of proof. So what you do is, it's the only time you see it can be recast into infinite dimensional Hamiltonian system. Okay, but I want to say the construction does not rely on the Hamiltonian structure. Okay, so H, if you take your Hamiltonian H u bar equals to some epsilon Laplacian plus V j prime uj prime bar. Everyone knows this part, yeah? It's the harmonic oscillator part. Plus delta p plus 1 sum over j uj p plus 1 uj bar p plus 1. If you take this as your Hamiltonian, which I can define to be H0 u bar, the linear part, plus delta H1 u bar. Okay, so this is just a coupled harmonic oscillator. Then you see that 2 is nothing but this following Hamiltonian equation of motion, I u dot equals to 2 partial H partial u. Okay, this is standard. And with u equals to the more usual canonical variable, u bar is p minus iq. Okay. Okay. So here's the remark. I verbalize, write it down. So do not use Hamiltonian structure. The Hamiltonian structure is only used, Hamiltonian structure used to ensure the real reality of omega, okay? The modulated frequency. You want it to be real, right? So that's the only time that the Hamiltonian structure is used. Otherwise, it's completely, we don't use it. So what do? We use, so two, so I call this 3. We use 3 as an ansatz, so we look for a solution of this form. Okay? If we look for a solution of this form and you plug it into the equation, and out comes that you have to solve the following equation, which is n dot omega, so this nonlinear Schrödinger goes to the following equation, n dot omega plus epsilon Laplacian. So I'm going to put a subscript j for operators that operate on ZD, the original spatial variable, plus Vj u hat jn plus delta partial h1 partial u bar hat jn equal to 0. So where n is in z nu, the harmonics direction, and j, the original spatial direction. Okay? And we want to solve it with the constraint that u jk ek equals to ak. That is, that if you come back to this picture, on this picture, I say that on these 4 sides, my amplitude remains the same. Okay? It's the frequency that's going to be modulated. And on the rest, you have to determine the frequency. No, sorry, determine the amplitude. Okay. So u hat jk ek is ak. K equals to 1 to nu. And the singular set, I mean, the singular set is just where you have the eigenfunction, like eigenvalue for the linear problem. Okay, that's your singular set. Okay, so now what you do is you do a Lyapunov-Schmidt P and Q decomposition. P and Q decomposition. So first of all, I write the Q equations. The Q equation, there are only null of them, okay? The new equations, they're new finite system. And that's obtained by just restricting the system to the singular set. So you have n dot omega plus epsilon Laplacian j plus vj u hat j k minus ek plus delta partial h1 partial u bar hat jk minus ek equal to 0. You just have to verify this equation. On that, the amplitude is fixed. And the remaining equations form the infinite system of P equations. So this is so that's the Q equation, and the P equation is the case. I just rewrite the equation again. Epsilon Laplacian j plus vj u hat jn plus delta partial h1 partial u bar jn equal to 0, jn not in S. Okay, recall that. Okay, to etch this, I guess, in your mind, you think of this following thing. In the linear case, this is satisfied. This is trivially satisfied because the amplitude is 0. Okay? In the nonlinear case, now you have to solve this. You solve this, and you plug it back in to make it consistent, if you like. Okay? This gives you the frequency modulation here. Okay, but I just make a little remark. There's a remark here. Then use implicit function theorem, but there's a little subtlety here, is because you can only construct the solution on the Cantor set. So what you have to do is you have to also control the derivative of the solution. So you extend the solution to the whole parameter space. Then you do inverse. Then you use the standard implicit function theory. So there's a little subtlety here. Now I'm going to go to the P equation, and we solve it by using the Newton scheme. So the main thing is really to solve the P equation. Okay? Then you plug it back, and here this is a multi-scale argument. P equation plus Newton scheme. Remember that I've taken a particular nonlinearity, which is the form u hat p u. Okay, so both u and its complex conjugate are involved, right? Because of this term. So I duplicate the system to include also the complex conjugate, and you have the following system of equations: n dot omega plus epsilon Laplacian j plus vj u hat jn plus delta. So I have u hat, and v hat corresponds to the complex conjugate. Okay, you want to have a closed system. U hat delta, u hat convolved with the power p convolution, p times equals to 0, and its complex conjugate minus n dot omega plus epsilon Laplacian j plus vj V Jn plus delta U hat convolved with V hat P convolved with V equal to 0. Okay. So what you want, I'm going to call U hat, V hat, I'm going to call it Y. So our task is to, and I'm going to call the left-hand side F, to find Y such that Fy equals to 0, right? Of course, I start with Y equal to 0, right? I'm on the complement, where for the linear problem, Y is 0, yeah? So I start from Y equals to 0, Y0 equals to 0. So the Newton scheme, I guess everyone knows, yeah? So, sorry. So you have Fy like this. You want to find this root. You start from somewhere, right? You do the tangent. It's just that, okay? And so what you want is you want delta at I plus 1 stage of Y, which is yi plus 1 minus yi equals to minus f prime yi inverse f of yi, right? Okay, so this is true. This is true. And what is fyi? So, not much time actually. So, and then fyi is fyi minus 1 plus a linear part yi minus yi minus 1 plus something which is quadratic, right? yi minus 1, yi minus yi minus 1 square, right? I mean, the Newton scheme is constructed so that this part is 0. Okay? So now you substitute this into there. What you get is that this is minus f prime yi inverse. So this is good. It's the crucial point, actually. You get yi minus yi inverse square, okay? All right, this is the crucial point. Here it's linear, right? And this is square now, okay? Okay, so that means that you can suffer a rather bad small divisor problem here, okay? And you still gain. Yes, this is the crucial point. Okay? The convergence here is double exponential, right? So what is f prime y? F prime y is the linearized operator, yeah? For example, if you forget about this, it's just that. Okay? It's inevitable that you have small divisor, but luckily the Newton scheme has double exponential convergence, so you can have a bad factor here. Okay, so this is the crucial point, actually. So for example, f prime yi in the simplest case is just, let's say, n dot omega plus Laplacian. So to zeroth order approximation is just this. I forget the nonlinear coupling, okay? In this case, now actually it's very interesting. In this case, you see that, okay, so this part and this part, they commute, okay? Because this operates on ZD and this is on Z nu. Okay, the two-part commute. So in this case, it kind of, you know that I just need to cut, I have this omega, which is a parameter I just cut in omega. Okay, so this also explains a bit why you have to cut. You see, you have to avoid the resonances. Okay, so now I come to the crucial point, which is the control of small divisor coming from inverting this linear operator. So I do that. So this is where actually things diverge from KAM method. Okay, is that we only try to invert this. We do not try to diagonalize it. This is the crucial point, actually. And this is the reason why we can go beyond d equals to 1. because it's hopeless to keep track of eigenvalues. But, of course, there's a price to pay, because if you don't diagonalize, you have to deal with more general polynomials and not just products of monomials. So T, so this is the control of small divisors, yeah, in Tn. Tn just means that, I cut, all right, I cut. So that T equals to n dot omega plus epsilon Laplacian j plus Vj plus delta. Here I'm just going to put a Laplacian tilde, which acts in the n variable, you see, because I have a convolution, okay? It's going to expand, but just think of it as tridiagonal. So this is achieved by, so small to control, small divisor. This is achieved by successive incision in omega, okay? The primitive step you see already, you're cutting omega, okay? And, but when you go to higher order iterations, it's not as going to be simple as that, okay? The crucial point, what we use is that we want to avoid small divisor correspond to determinant t close to 0, right? Obviously. Okay. So now the point is, how do you control the determinant? Two properties. One, determinant t is a, very important, is a rational function in omega. Is a rational function. Okay. So the set that determinant t is, let's say, less than some small number is a semi-algebraic set. So the degree of the semi-algebraic set is determined by the size of the matrix, that is the size you cut, determined by n. Okay, so so then you use results from real algebraic geometry, actually very recent results, around circa 2000 of results of Basu, which gives you the number of connected components. Okay. So this is one crucial point, okay? It gives you the number of connected components. Actually gives you a bound on the number of connected components. We don't know where the singularities are. We just know that they cannot be more than a certain number. So you have given up, huh? You don't have a choice. You give up, okay? You just control the number. So this is the topological aspect of the singular set. Topological. This is the topological aspect, okay? Which is crucial. This is why people were not able to go beyond one dimension. It's hopeless to keep track of the eigenvalues. So you just have to give up, okay? Just say that I only know there are only so many singularities. So that's the topological aspect. The other aspect is the measure aspect. I started, I think, 2 minutes late, so and I'll try to be 1 minute early. So the measure aspect. So I forgot my operators are n dot omega plus epsilon Laplacian j plus Vj. So here, there's a technical device. What you do is you add a fictitious theta, okay? in the end, you remove it. I add the theta. I added another parameter, all right? You see, I remove it. So then you control measuring theta. So I move theta so that I avoid the singularities. Okay, so this is purely technical device. I'm almost there. Okay, so here what you need to use, you use some Cartan type of theorem. And again, there's some kind of multi-scale analysis I don't want to go into. But anyway, you get into the measure aspect of theta. Now you protest, my original problem is when theta equals to 0, right? So what you have to do is, you have to, afterwards, the way you remove, and after so you do this, then you have iteration. So what I want to say, the measure aspect coupled with the topological aspect plus the Diophantine frequency tells you how many singular points you can have, okay? Because you know how many intervals you can have, and then if you have Diophantine frequency, you know how many integers can live in there, right? Because you're looking at n dot omega, okay? I don't want to get into it. So okay, so in the end, the last thing I want to say is you want to add this theta, so I have to remove theta, which means in effect that you restrict to theta of the form n dot omega, right? Because if I restrict theta of the form n dot omega, that means I'm just doing some translation and remaining at theta equal to 0. So here, again, you use the fact that you have a semi-algebraic set, okay, of small measure, okay, evidently of small measure. This is of small measure. And what you know in this case actually is kind of rigidity of the semi-algebraic semi-algebraic set. They're L-shaped, i.e., they are of small measure because it's essentially flat if you remove a set. Okay, so therefore, think of semi-algebraic sets like this, and n dot omega for n very large is vertical, so the intersection is very small. But it's getting into detail. So when you combine all of this together in iteration, you get the final result. Okay, so you construct. So there are two main things here. Is that contrary to KM, you don't diagonalize. When you linearize, you keep the whole thing. So therefore, you have to deal with the determinant, therefore general polynomials. So the point you use here is that the singular set is semi-algebraic. So you can have control over its topological aspect, and measure aspect, and everything else. Okay. So the last thing I want to say, so now the question, on a kind of a physicist question, what do you do? When you prepare data, you don't choose a counter set of frequencies, right? So what can you say about arbitrary data? So the arbitrary data, it's actually going to diffuse. It's reminiscent of Arnold diffusion. So the question is, can you have a control? And I think with some cheat, you can say that it does not diffuse faster than any polynomial. Okay, so that's. But I stop here. I think I've.
Questions?
Well, two naive questions. The first is, do you assume Diophantine conditions
Yes,
on,
yes.
On the VK, on the parameters?
Yes,
Okay.
yes.
And the second is,
It's not a naive question because you have to go through all the iterations to make sure
the same as
to make sure that the error you accumulate lies within the margin. Yes.
And the second one is the relation. Do you have a condition about a relationship between D and P? The power of your result holds without any condition about the relationship between the dimension and the power of the non-linearity?
No, I think this is because to begin with, I am with the problem with the parameter. So it's probably somewhere in these things that I've cut away. That
More questions? If not, thanks again.